Hello everyone. In today's lesson, we're going to begin chapter 4, and we're going to start talking about discrete probability distributions. So section 4.1 is going to be about discrete probability distributions in general, followed by a specific type of probability distribution called a binomial distribution, and then chapter 4.3 will be on the geometric probability distribution. So first things first, let's actually do a couple new definitions and some old ones. So the first definition is a statistical experiment, which is any process or study which results in collection of data, the outcome of which is unknown, right? And that's the big thing with whenever we're dealing with probability is we have unknown outcomes. We might know what are possible outcomes, but we don't know what the actual outcomes are until the experiment is done. Hence why, we have things like random variables, which we don't know the outcome for until the actual experiment occurs. And any characteristic that can be measured or categorized is called a variable. If a variable can assume a number of different values such that any particular outcome is determined by chance, this is called a random variable. So like I just said, a random variable is a variable which represents some specific characteristic of our data that we do not know the outcome until we actually gather the data. For example, going back to probability, if I roll a die, I might know that the variable x is the outcome, which could be 1, 2, 3, 4, 5, or 6. But it's a random variable because until I actually roll that die, I do not know what the outcome is. Once I've rolled it, now I have an actual outcome. Now, our random variables can either be discrete or they can be continuous and are commonly represented with capital letters. So generally, we'll do things like x, y, or z. Now, we've already defined what it means to be discrete. We've defined what it means to be continuous. This chapter is going to be focusing on probability distributions of discrete data, which means that our data has gaps in it where there's nothing in those gaps, right? So this would be something like whole numbers, 1, 2, 3, 4. You're either 2 or you're 3. There's nothing in between. So you can't get 2.3, you can't get 2.7. It's just 2 or it is equal to 3. So a discrete random variable can assume only a finite or countable number of outcomes. So generally, especially when we're doing counting type numbers, this would be things that, of course, you can count, right? If we're counting the number of cars in a garage, number of students in a class, these numbers will be finite. But discrete numbers can also be what are called countably infinite. So this means that they still have the gaps and there's a consistent method that they grow. So an example of this might be the natural numbers, right? 1, 2, 3, 4, 5, 6, and it can go on forever. There's no end to it, but it's still considered discrete data because we have those set gaps, and we could kind of think of some method that we could count them if we had an infinite amount of time to infinitely count them. So an example of this would be things like the number of phone calls made in a given day, the number of employees who use elevators, things like that, right? Generally, again, a lot of counting type problems. A continuous random variable can take any value. It's on a continuous spectrum with some particular interval or continuum. So what does this mean? It means that when we have discrete values, they have gaps. So it'd be something like 1, 2, 3, 4, and so on and so forth. Or it could even be decimals. 1, 1.1, 1.2, 1.3, 1.4, so on and so forth. So both of these, they have some specific set gap between our numbers, but they don't have to be whole numbers. So there's nothing in between these values. So between any of these, there's nothing that exists. You're either 1 or in this case 1.1. In this top example, you're either 1 or you're 2. There is no in between. For continuous data, we have a continuum. Think of a number line that you've learned about previously. You have this line which represents all of the possible values. And in between any two values, there are an infinite number of values. So let's say, for example, that this is 0 and this is 1. Well, this means that I could get an infinite number of values in here. So let's pick the easiest one. Let's split it in half. Let's say that this is 0.5. So now focus on this bottom interval, 0 to 0.5. And I could again split this in half, 0.25. And now I'll look at this lower interval, 0 to 0.25. And I could, again, split this in half, 0.125. And I could split this in half, and then this in half, and then this in half. And basically, I could do this on forever. So between any 2 points, there's an infinite number of points. So I could have picked any other point. I could have picked somewhere up here. I could have picked somewhere here. And even if I pick 2 points that are right next to each other, there's an infinite number of points in there. So it's a continuum. And this is really going to affect how we use our probability distributions and think about our data. Because in this case, there's a set method to it with nothing between them. So again, 1, 2, 3, 4. This one you have to take into account that there's an uncountable number of possibilities. So some examples of a continuous random variable would be things like weight, time spent on phone calls in a given day, height, speed of a car, age of a person, pretty much anything that we are measuring from some starting point 0, and it's any possibility up to whatever point we get to, that would be something that is continuous, right? If I'm looking at how much rain falls in a given month in some city, well, guess what? That's continuous, because even if it goes from 0 to 6 inches, it had to hit every possible amount of rain in between there, right? If we're talking about the rain gathering methods to measure how much rain we get. This leads us to our next definition, which is a probability distribution. So a probability distribution applies the theory of probability to describe the behavior of a random variable. So an example of a discrete probability distribution could be describing the behavior of rolling a single fair die, or perhaps 2 fair dice, something like that. So it is an assignment of the probabilities to a specific value. This is the discrete case, or of a range of values for the continuous case, right? Because if I have discrete case, I might have, again, 1, 2, 3, 4. I can say, what is the probability that I get a 1? What is the probability I get a 2? What is the probability I get a 3? When we have continuous data, because there's an infinite number of them, which we'll talk more about this in chapter 5, we would have to ask a question more about what is the probability I get more than this, or less than this, or between these two values. We have to have some interval for our probability questions. So every random variable has a corresponding probability distribution, and each value of the random variable has an assigned probability where the probabilities must sum up to 1. So I'm actually going to redefine our probability distribution a little bit. And it basically needs 2 key factors, which are, for a probability distribution, we need 1, every possible outcome, and 2, we need all associated or respective probabilities. So what does this mean in practice? Okay, going back to my rolling a fair die example, I would need all of my possible outcomes. So if I did this experiment, what could happen? In this case, my sample space would be equal to 1, 2, 3, 4, 5, and 6. And then I would need the probability for each of those. So I would need the probability of 1, and I would need the probability of 2, I would need the probability of 3, the probability of 4, probability of 5, and the probability of 6. And you may have noticed I put them equal to each other. This is because if I had a fair die, then I know that the probability of each of these would just be equal to 1 over 6. So in this case, I actually have a probability distribution. I know all of the different outcomes, and I know every probability associated with those outcomes. And some of the things about our probability distribution is that the sum of our probabilities must be equal to 1. And that's because the sum of these probabilities will be the probability of the sample space, right? Because if we take probability of getting a 1 plus probability of getting a 2 plus probability of getting a 3 plus probability of getting a 4 plus probability of getting a 5 plus probability of getting a 6, this accounts for all of the possible outcomes. and they are mutually exclusive from each other. If I roll a die and I tell you that I got a 2, that means that it could not have been a 1, a 3, a 4, a 5, and a 6. So therefore, they are mutually exclusive from each other. They make up all possibilities, meaning that they are just equal to the probability of the sample space, which is equal to 1. And this is why it's so important that you have all of the possible outcomes, because if the probability of all of your individual probabilities added up together does not equal to 1, it means that you are missing some of the possible outcomes. So now we're going to talk about how do we find our mean or expected value of a discrete distribution and our random variable associated with it. So the average value assumed by a random variable is known as the population mean. The dispersion of those values relative to the mean is our population variance. And of course, if we take the square root of that, just like we did in chapter 2, this would be our population standard deviation. So the mean or expected value of a discrete population probability distribution can be calculated using expected value of x is equal to mu, because it's the mean, it's the average, is going to be equal to the sum of every possible outcome, x, times its associated probability of x. So just to make this more clear, I'm going to write this as x sub I and p x sub I. When we were doing the dice example, the expected value would be the outcome 1 times the probability of getting a 1, plus the outcome 2 times the probability of getting a 2, plus the outcome 3, probability of 3, 4, and then you do this for all of the possible outcomes. And this is why you need those two pieces of information. You need all the possible outcomes and you need their associated probability. This will give you the average expected outcome, which is why we have this expected value. This expected value is what is the outcome that you would expect to occur on average if I did this experiment over and over and over again. So let's say that we do the die example. Then if I were to take my expected value of x, this would be the outcome 1 times the probability of being 1, which is 1/6, plus the outcome 2 times probability of being a 2, which is 1/6, plus the outcome 3 times the probability of being a 3, which is 1/6, plus the outcome 4, which is multiplied by the probability of being a 4, which is 1/6, plus the outcome 5 times its associated probability, plus the outcome 6 times its associated probability. Now, I'm going to just rewrite this really quick to make it a little bit easier to calculate. All of these things are divided by 6, so I'm going to write this just as 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. And then, of course, if we were to add all these values up, let's see, 10, 15, 16, 17, 18, 19, 20, 21. So I get 21 divided by 6, which, of course, is going to be equal to 3.5. So what does this mean? That means that every time I roll a die, the average of all of the possible dice rolls that I could roll would be a 3.5. That means that if I were to roll this die one time, I could get pretty much any of these. They're all equally likely. If I roll the die another time, and another time, and another time, that means that I expect some to be in the lower end, 1 and 2. I expect some to be in the upper end, 5 and 6, and some to be in the middle, 3 and 4. And then what's going to happen is as you roll more and more and more dice, the 1 and the 6 are going to kind of balance out. The 2 and the 5 will start to balance out. The 3 and the 4 will start to balance out until it basically converges on average, I would expect to get a 3.5. Meaning that if I have some dice game where I wanted to have the winnings based on the outcomes, then the casino, for example, which will see many of these dice rolls, would probably want the value to be somewhere in the 3.5 outcome range. Now, this is dependent on the law of large numbers, meaning that if you're playing that dice game, in any given dice roll, a discrete probability distribution, every value is equally likely in this case. So it doesn't matter whether you're rolling the die once. If you rolled a 6, you roll it again, your probability of getting a 6 is exactly the same. But it means that given many, many, many trials, which would be beyond what a single person could ever do, but if you have something like a casino, this is actually how they make money. So let's go back to when we were rolling 2 dice. When we were rolling 2 dice, we had a sample space S equals, and we have to think about what are the possible outcomes. Well, I could get a 1 and a 1, which would give me a 2. I could get a 1 and a 2, or a 2 and a 1, which would give me a 3, 4, up to 12. So I have 11 possible outcomes that I could get when I roll 2 dice. So let's actually remember what our probability of each of these outcomes are. So if you remember, the probability of 2, which is equal to the probability of being a 12, is just 1 over 36. The probability of getting a 3, which is equal to the probability of getting 11, is equal to 2 over 36. The probability of getting a 4, which is equal to the probability of being a 10, is equal to 3 over 36. The probability of getting a 5, which is equal to the probability of getting a 9, is equal to 4 over 36. The probability of getting a 6, which is equal to the probability of getting an 8, is equal to 5 over 36. And then, of course, the probability of getting a 7 is equal to 6 over 36. This means that on any given dice roll, these are the probabilities that you will get any individual outcome. So the probability that if you roll 2 dice, you will get a 2 is 1 out of 36. Or probability of getting a 12 on those when you roll those 2 dice is 1 out of 36. Probability of getting a 3 or an 11 is 2 out of 36. 4 or 10, 3 out of 36. 5 or 9, 4 out of 36. 6 or 8, 5 out of 36. And the probability of getting a 7 is 6 out of 36. So 7 is the most likely outcome on any given dice roll when you're rolling 2 dice. Which is why, if you ever play the game craps, the first round you lose if you get a 7. And then, of course, they also have an 11 included there. But they chose this number because they know you are more likely to roll a 7 than any other number. And then what you could do is if they wanted to determine what is the average outcome you would expect someone to roll with these dice, then you would just take every outcome. So the expected value of x would be 2 times 1 over 36 plus 3 times 2 over 36 plus 4 times 3 over 36 plus ... And you would do this all the way until you get to 12 times 1 over 36. And then with this, you could figure out what the expected value is. So the expected value of this problem is equal to 7. So you can see that if they were to play this game many times, to the point where you start to encounter the law of large numbers, on average, the average of the rolls would be a 7. And your most likely outcome on any given roll is going to be equal to 7. So this is actually why that number is selected for you to lose the game on and the casino to win, because they know exactly what the likelihood and probability is of any given outcome. Now, another place, again, in gambling where you might encounter expected value is anyone who's ever played poker. In poker, they actually have a different term for it, and this is called pot odds. So the way pot odds work is that, let's say that I have a pot which has $300 in it. And I could make a bet for $50. But my probability of winning, I'm going to call this probability of W for winning, is only 1/3. Meaning I basically have a losing hand. I will lose 2/3 of the time. I will win 1/3 of the time. Should I make this bet? Now, the way pot odds work is you would want to then say, okay, what's my expected outcome if I were to play this hand? Well, the thing is, if I were to bet this $50, I would have a pot of $350, let's say, and I would win $300 because, of course, I had to put in 50. So that means that I could win $300 times 1/3, the probability that I were to win. If I lose, well, I'm losing $50, right? This is what I'm actually betting to be in the hand. So I could get minus $50, and my probability of that occurring is 2/3. So in this case, 300 divided by 3, this is going to be equal to 100 minus 50 times 2/3 would be about $33.33. This means that every time I were to play this hand, I would expect about $66.66 of winnings, meaning that it's actually what's called a positive pot odd, meaning that it is worth me making this losing bet because if I win, I win $300. If I lose $50. So if this event were to occur again, the same exact situation, which obviously in the real world it doesn't, it means that I would only have to win 1/3 of these hands and I'm making positive money. So this is actually used in poker by poker players. They call it pot odds, but it's just the expected value. It is based on what the possible outcomes are. I could lose $300, or I could make $300, or I could lose $50. And the probability associated with it, I would win $300 1/3 of the time. I would lose $50 2/3 of the time. Is it worth me spending the money to stay in the hand for this outcome? Because I know that I will lose 2/3 of the time. I will only win 1/3 of the time. But because I win so much more than I would lose, it actually ends up being a positive expectation. That means that it is worth me risking the money in this case on a losing hand because the outcome outweighs the loss of however many losses I would have if I were to repeat this experiment. Now, of course, in the short run, anytime you play this, you are at the will of probability, which has randomness. So you might lose more than 2 out of 3 of these hands. You might win more than 1 out of 3 of these hands. In the short term, it kind of goes out the window. But the idea is that what is the correct play to make? And it's based on, if I were to repeat this, what decision should I make? So now let's talk about the variance of our discrete probability distributions. So the variance for a discrete probability distribution, so variance of x, which of course we can just write as sigma squared, this is going to be equal to the sum of my outcome x, whatever outcomes I have, minus the mean, which if you remember, the mean is just our expected value that we just calculated. We'll square that, and then we will multiply by each associated probability. So as before, what I'm going to do, just to clarify a little bit, is this is x sub I, this is p x sub I. So as an example, using our original 6 dice example, we had s equals 1, 2, 3, 4, 5, and 6. And we had that the probability of each of these, I'm just going to put it as the probability of x, was equal to 1/6 because they were all equally likely. We said that the expected value, mu, was equal to 3.5. So to find the variance for this, it would just be sigma squared is equal to the first outcome, 1 minus mu, 3.5, squared times the probability associated with getting a 1, in this case, 1/6, plus the second outcome, 2 minus 3.5 squared times 1/6, plus the next outcome, 3 minus 3.5 squared times 1/6, plus 4 minus 3.5 squared times 1/6, plus 5 minus 3.5 squared times 1/6, plus 6 minus 3.5 squared times 1/6. And this would give us our variance for this rolling 1 die experiment. Now, one thing I want to point out is that in all of these examples, I am using outcomes oftentimes that are the same because they're very easy to conjure up, rolling a single die. But notice when we did 2 dice, we didn't have the same probability for each one. So if you did something like that, it would actually end up being something more like this. You would have the probability of getting a 2 minus, and then whatever that outcome is, squared, and the probability of getting a 2 was 1/36, plus, and then you'd get the probability, or the outcome 3, minus whatever that expected value of it was. Oh, that's right, we said it was 7. Squared, and then this one would be 2/36, plus 4 minus 7 squared, 3/36, and then you would just do this until you get to 12 minus 7 squared times 1 over 36. And this would give you the variance of rolling 2 dice. So I wanted to point this out because in this first example, they all had the same probability. And I don't want you to get under the impression that your probability doesn't change. This is why it's P x sub I. It's the probability with that particular outcome. So x sub 1 is 1. So this is the probability of getting a 1. X sub 2 is 2. This is the probability of getting a 2. X sub 3 is 3. This is the probability of getting a 3. When rolling 2 dice, x sub 1 was 2, meaning we had a probability of 1 over 36. When x sub 2 was 3, which meant we had a probability of 2 over 36, and so on and so forth. Now, if you want to get your standard deviation, you just could take this entire thing, you take the square root of it, or if you found the variance first, you could just have sigma equals the square root of whatever you got when you found sigma squared. So the standard deviation is just the square root of the variance. Now remember, the reason we have the two different values, even though they're just a scaled equivalent of each other, is variance, we square the values because notice when we were doing this example here, we're rolling 1 die. We had 1 minus 3.5. That's going to give us a negative. 2 minus 3.5. That's going to give us a negative. 3 minus 3.5. That's going to give us a negative. 4 minus 3.5, positive. 5 minus 3.5, positive. 6 minus 3.5, positive. If we were to take these probabilities, sum it, we're actually not getting how much the data varies because we would be counteracting the positives with the negatives. So what we do is we square, so we get all positive values. So it is the squared deviation from the mean. To bring it back down to the scale of our actual dice rolls, this is then, we take the square root, which then puts it back in the scale of our actual dice rolls, right? So this one, you're going to get some value that is kind of outside of what you would expect for a dice roll. But this one will say, okay, it's something like standard deviation of 2 or something like that. Off the top of my head, I don't know what the standard deviation is, but we could easily calculate it just by doing this. That's it for our introduction to discrete probability distributions. Now, I will make another video with some examples, but I want to make one more comment before we move on to actually calculating different specific probability distributions. And that is, these methods that we've looked at today work for any discrete probability distribution, whether it's binomial, whether it's geometric, whether it's Poisson, it will work for any. If you have the data, which means you know the possible outcomes and you know the probabilities, you can use these methods we looked at. The expected value, which is just the mean of the discrete probability distribution, the variance of your discrete probability distribution, and the standard deviation of our discrete probability distribution. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.